Okay, so for this PowerPoint, we're going to look at volcanoes. And so now that we have some information about the different rock types, we want to focus on some of the hazards. So for the next two modules, we'll discuss volcanoes. So it's going to be broken up into two parts here. We're going to focus on this PowerPoint on just the volcanoes themselves. So you've got the history about where we get magma and how potentially we get that material to the surface. When that happens, we can get volcanoes. Now, the type of volcano we get is going to be contingent upon its composition. And so we're going to go through the different types of volcanoes we can get, and we're going to relate that to composition, and of course, back to our plate tectonics that we talked about. And then we want to talk about, why they're different and a little bit about how they erupt. So for this PowerPoint, we're going to focus mostly on different types of volcanoes. So there's small ones, there's big ones, there's ones that erupt super violently, there's ones that are very kind of low explosivity when they erupt. So we want to investigate those, associate the properties of the different volcanoes with each one. And then in the following PowerPoint, in the next module, we'll talk more about the hazards that are associated with each. And of course, that's related to their explosivity, which is of course related to their composition. So for this one, it's more about identifying the types of volcanoes that we see, how they get there, where do they form in relation to our planet and plate tectonics. And then, like I said, the following PowerPoint and module, we'll talk more about the different hazards that are associated with each and potentially how do we mediate those hazards? How do we keep them from being so devastating, right? So that's what we're going to do in this PowerPoint. So let's go ahead and get started.
Okay, so for this module, this is Volcanoes 1. We're going to talk about the basics of volcanoes before we get into the crazy hazards. And so in this PowerPoint/video, we're going to discuss the different types of volcanoes we get. I'll mention some of the hazards that are associated with each, and we'll talk about why they look the way they do, why are they different, all those kind of things. And then in the module that is titled Volcano 2, we'll focus more on the hazards, like what are they specifically, how do they impact society, how do we mitigate some of those. So that's kind of where we're going with this story here. So what I'm going to give you this kind of quick overview here. So this is kind of the story that we have to keep in mind when we're talking about volcanoes. So first is this idea of composition is super important. And so that was introduced, we talked about igneous rocks. So remember the term mafic, intermediate, and felsic are composition terms. In general, we could assign some properties to that, right? So mafic are the dark colored rocks. Why? Because they have a lot of iron and magnesium, and that makes the rocks dark because those make dark colored minerals. Minerals make up the rocks, and so if the minerals are dark, the rock is dark. So that's one thing about the mafic. And then we could say about felsic, because there isn't a lot of iron and magnesium, they make lighter colored minerals. The rocks overall are lighter. And then, of course, we have something in the middle. Now, remember, there are multiple types of igneous rocks, right? The intrusive stuff, big crystals, and then the extrusive stuff, which is the small crystals. So if we're talking small crystals, we would say this is black in color because we can't really see the individual crystals. So overall, the rock looks black. Felsic looks kind of light in color, so that can be tan or off-white. And then the intermediate would be kind of like a gray. If we're talking intrusive igneous rocks with big crystals, this still would look pretty much all black or mostly black because it'd have a lot of black minerals. The felsic would still have some black minerals. So here we use kind of a percentage. So the low percentage, so there's a small amount of black would be felsic. The kind of 50-50 black and white minerals would be intermediate. And that's how we would loosely identify the composition of igneous rocks. If you were handed a sample and you said, hey, what is this? Big or small? And then we could look at the color, and that would help us determine its composition. The other thing that's really important is silica content. So SiO2 is actually the chemical formula for quartz, which is a mineral that is made up of SiO2. It's pure, right, quartz, and a lot of SiO2 is bonded to other elements to make minerals. So there's a lot of SiO2 in the minerals that make up the rocks. But if we compare The mafic rocks have a low silica content, or SiO2 content. There's not a lot there. And the felsic have a lot of SiO2 in their minerals and their overall composition. So we can use that to determine how a volcano will look and how it will erupt. Okay, and so here's some other properties that we associate kind of with these compositions, right? So these melt at high temperatures, they have low silica, some of the kind of elements that are there. Here's explosivity, like how violent are they? Here's some volcano names that we'll discuss shortly. And here are some places where we get these types of volcanoes. So remember, when we talk about magma, so magma is the molten stuff inside the earth. Remember, you can't just go into the earth and be like, oh, look, the mantle, it's all this soupy liquid. No, 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 right? The mantle, at least part of it, is hot enough to be gooey. We're talking silly putty, right? It flows, but it is not a liquid. In order to get magma, we have to melt it. It has to be a complete liquid, right? And that doesn't happen everywhere. In certain spots, under certain conditions, we can partially melt the mantle. Okay, so another term I'm going to throw at you that we introduced in igneous, but is the term ultramafic. What? So that term would sit up here, just meaning it has even lower silica, even more iron and magnesium. That's what the overall mantle we think is made of. But when these processes occur in the mantle that cause some melting to occur, remember, the mantle, like all other rocks, the mantle rocks are made of minerals. So not all of the minerals in the mantle will melt, only the ones that have a lower melting temperature. So I don't melt all the minerals that make up the mantle, only some. This is what we call partial melting. And that partial melt, when it forms and kind of gathers together, is initially going to be mafic in composition. So we start out with these mafic melts, and this is in general. There's exceptions to every rule, of course, because there's weirdness going on, but in general, when we start out with magma at depth, it is mafic. Now, as it moves to the surface, it can interact with a ton of things, different rock types. It can slowly cool and then quickly cool. It can partially cool and lose some of the, minerals and then still be molten. Doing this changes its composition as it moves. And so we can start with mafic and get any of these other compositions. Mafic, intermediate, felsic, all that kind of stuff, okay? So still kind of an overview. And then the last overview I'll throw at you is, of course, remember, where do we get these melts? In general, convergent plate boundaries. There's a process here. Now, this is a picture of an oceanic plate, right? It is subducting under a continental plate. And there's a process here that causes the mantle to partially melt. What's its composition here? It's mafic. But as it moves through this material to the surface, in this particular image, it is interacting with a different composition material. This is very felsic. And so I can mix them. Mafic on one end, felsic on the other. I can get something in the middle. That's a possibility. I can also just get felsic. Why? Because I have felsic material. What if it doesn't mix very well? But this material that's rising is super hot. It acts as like a flame, and it can just melt some of the felsic material. And so now I just have a felsic. That's a possibility. There's even a chance that if this is highly fractured, I can allow a lot of the mafic stuff to ooze its way through to the surface without interacting very much, and even get a mafic melt. But in this situation, in this particular diagram, generally we say when we have an oceanic plate subducting under a continental plate, there is some mixing here, and we generally get intermediate type of igneous material. So we get intermediate volcanoes, we get intermediate rocks being formed. Okay. Now, if this is an oceanic plate, so I can have two ocean plates collide. We know that from past lectures, right? Subduction happens. I have mostly mafic mixing with mostly mafic. I get mostly mafic rocks at the surface because there isn't a lot of stuff to alter the chemistry of the rocks. Although we can have some cooling weirdness that changes the chemistry, so you can get some variety there. Just not as big a variety as we would see in this situation. And of course, other places we get melting, divergent plate boundary. What's the composition of this magma and this lava? Well, we partially melt the mantle. We always get mafic. It rises to the surface here, and it cools and crystallizes. We get mafic. Once again, this is all mafic, so there's not a lot of variability here because I can't really mix. So I generally get mafic here at divergent plate boundaries. And then, of course, in our last example, did I skip something here? Nope, I like that. Okay, we have hot spots. And so these are sometimes called mantle plumes, and they can form for a variety of reasons. Some are very deep, some are more shallow, but it's this rising mantle material, and because it's rising, it decompresses and it can start to partially melt parts of the mantle. Now, what do we get when we partially melt a mantle? Well, we get mafic melts. But what happens? Well, it depends. What's above it? There are times where it's interacting with a continental crust, which is very felsic. I have a mafic melt and I have felsic. I can get almost anything here. I can mix and I can get intermediate. I cannot mix very well and get felsic, or not mix very well and get mafic. So I know that can be kind of confusing. So we try in a 101 to kind of put things in buckets and say, look, if you have subduction with ocean continent, guess what? You usually get intermediate. And if you have a divergent plate boundary, you almost always get mafic because there's not a lot to mix with. If you have a hot spot under the ocean, there's not much variability there because the ocean plate is mafic and I melt is mafic, so I generally get mafic. Think the Hawaiian Islands. That's a hot spot under the ocean, and I get lots of mafic volcanic material there. If it's a hot spot under a continent, now I have some choices here. Typically, because we reference something like Yellowstone, which is a hot spot under the continental crust, what do we get there? We tend to get very felsic material because there isn't a lot of mixing going on, but the hot mafic magma that's rising is heating the continental crust, causing it to melt, and we get a lot of mafic or felsic material there. Can we mix some there? Sure. But that's kind of the kind of positions we put these things to keep it more simple. Just want you to be aware that the reality is there's some variability, right? Okay, holy cow, that was a long intro. So look, what we want to do is identify some of these volcanoes, some of their features, and associate them with compositions and things like that. So here's a picture of Mount St. Helens. Everybody's happy, it looks lovely, and then oops, okay. So we had a fairly violent eruption here. And so would we expect that from this type of volcano? We would. Why? Because of its composition, we know something about how it looks and also about how it erupts. This lava magma in an intermediate volcano is fairly thick, which means that it doesn't allow gases to move through the magma very easily. And so pressure can build. And so why do we have these explosive things? Well, one of the main things is water in the magma. So I know it sounds weird to think that water can exist within molten rock, but remember, we're not talking about, buckets or bottles of water. We're talking about, microscopic water, water that's attached to different minerals and things like that. It's still water. And so then there's enough of it that it's spread out throughout the magma chamber and also pressure, right, is changing when water will turn to steam. And so when we change the pressure, we can change the water to steam, and that takes up more volume, and that is a pressure change that causes explosive eruptions. Right? There's also other gases that are trapped in the magma, and because the pressure's high, they can't move until we lower the pressure. They expand. And so then that pushes the material outward and causes violence. And so besides this kind of how much gas and water is in the magma, it's the magma properties. Thick or thin is really what we're going to focus on here. We call that viscosity. And so once again, the reason that we focused on the compositions was that the compositions influence whether it's thick and gooey or kind of more runny. And so mafic, we're going to associate a low silica content with what we're calling low viscosity, right? So a low resistance to flow, which means there's no resistance. It flows easily. So look, when I have a volcano or magma that is very mafic, and I have water and gases in there, they can bubble out pretty easily. There isn't this big, thick, gooey stuff holding my gases and liquid in there. It allows it to escape, and so there isn't a big pressure buildup. So when these types of materials erupt or make it to the surface, they're not super explosive. Now they have pressure and power. So if you've seen some Hawaiian island volcanoes, right, they spew out and you have these lava fountains, right? There's pressure there. It's not like it's not powerful. But rarely do you have very big explosions with that. On the other end of the scale are the felsic materials. These are just the opposite. Lots of silica means high viscosity. So high silica content, high viscosity. What does that mean? It means the gases can escape. So as it moves to the surface and pressure decreases, I have water changing to gas, but it's trapped. It can't get out. I have other gases that expand. They can't get out. And so what does that mean? It means pressure starts to build, right? And then finally, when the pressure gets so great that the rocks above it can't keep it held together, there's a big blast that breaks through the rocks, totally releases all the pressure. And now these gases wildly expand and boom, I get a very violent eruption. So those are the felsic ones. And you might be saying, well, what about the intermediate ones? Well, like lots of things, the intermediate ones can do a little bit of everything. They can have some lower kind of violent eruptions and they can have some higher violent eruptions, right? Usually they're somewhere in between. They have the capacity to be very violent. And there's certainly some examples in the geologic past. Mount St. Helens was pretty violent. Now it was small when we look at the grand scheme of things, but that was a pretty violent eruption. And so they have the capacity to be very violent. So we want to be aware of those. So we're going to kind of look through these volcanoes, name them and associate them with their composition. And then, like I said, a little bit about their shape, a little bit about some of their hazards is what we're going to play the game with. And so where do we see a lot of volcanoes? Well, the main place that we do see those is subduction. So whether it's subduction over here where an ocean plate meets a continental plate, what would we expect here? We would expect intermediate volcanoes. And that is true because there is some mixing between the mafic melt that starts beneath the continent here, and then it mixes with the felsic continental plate, and we tend to get intermediate stuff. In other places, we can get more mafic stuff, but usually subduction is a big driver for where we get volcanoes. Now, we have hot spots, so over here in Hawaii is the big one. There's some weirdness going over in Iceland, of course, where there's not only a hot spot, but a divergent plate boundary. There's volcanism at divergent plate boundaries, no doubt. There's molten material coming to the surface. And there is a kind of a higher zone here. But because it's, remember, moving away, we don't always build these big, huge volcanoes. And of course, they're not as violent because they're under the ocean. Okay, so, but there are a few that make it to the surface, and those can be violent, of course. And so that's where we're looking for our types of volcanoes. And so our first one we want to introduce is called a shield volcano. So we're going to start mafic and kind of work our way down. So here, mafic, what does that mean to you? You want to think this is non-violent for the most part. So what does it look like? It tends to form these broad, flat kind of features. And why is that? The idea is that as it makes it to the surface, it's pretty runny. And so it flows for long distances. And so it doesn't build typically steep-sided volcanoes. And it looks like a shield, I guess, and that's kind of how it acquired its name. And so we usually get lots of lava flows. Once again, we can think Hawaii. Okay? And so we're not too worried about it being very violent because it doesn't have the power. So it doesn't explode very violently. Here's a crazy human standing next to a flow. Not particularly worried that they're going to die from an explosion. Maybe a hot blob of lava would fly. That would be bad, of course. And so we're not really worried. Where do we see these types of volcanoes? Well, shield volcanoes are typically at hot spots under the ocean basins. Now, like we say, there's always exceptions, but it's nice to have an answer. Like if I said, where do you see shield volcanoes? Hot spot under the ocean. Boom. That's your go-to answer, right? Does that mean they can't show up in other places? Well, no, but in general, that's where we typically see those. And of course, our favorite example is the Hawaiian Islands. So that's what we're looking for. Is this we're not worried about people dying from, no, we're not, but we're worried about lava flows. Certainly they can cause damage. We're worried about gases being released and things like that, but not this big violent eruption kind of stuff. So we feel pretty good about that. So here, broad flat, you can kind of see, right? This is the shape. And so potentially, visually, you could make some argument about, what the volcano type was based on its shape. It's broad and flat. Oh, that's probably a shield volcano, right? We even have some little ones here in Arizona. If you drive up from the valley, go into Flagstaff at Sunset Rest area, if you kind of look to the east, you'll see this little tiny hill. That's a small shield volcano, right? Called Joe's Hill. And so you can point that out as you go up to Flagstaff. So as we move down kind of our scale, right, we were at the top mafic, so low viscosity, low gas content. As we move down a little bit, getting below mafic, but not quite to intermediate yet, we see what are called cinder cones. Now these are shaped differently because there's a little more power here, a little more thicker material, so we do get a little bit of a boom, but not a very huge boom. Not that's going to impact hundreds of miles, more local. And that little kind of boom is what builds the shape and size of the volcano. So here we're taking mafic material and we're kind of shooting it out the top of a volcano. And what it does is it spreads out the liquid into these tiny pieces as they fly up into the air. And those pieces then solidify, they cool. And they fall back down. Think of like raining pebbles back down onto the ground. Well, because I have kind of a spot that's kind of spewing this out, it starts to build a little cone around this area that's spewing out these pieces. And we get cinders, and we get what's called cinder cones. They build up into these, round-shaped kind of conical things. I know what you see over here on the right. It's mostly made up of these little explosions that spew out this material that fly into the air, cool, and then fall back down. Certainly there's some ash, this really tiny stuff that gets up and kind of drifts away, but the main material that builds the volcano are these little pieces that fly up because there's some power here and they fall back down. Okay, and so these tend to be fairly small. Now, if you go up to Flagstaff, there's a bunch of them. And so they're all mafic. How can we tell? Well, the big thing here is color, and that would be true of the Hawaiian Island stuff and the shield volcano, right? Those rocks are very dark in color, and that, for our mind, is telling us mafic. So even if we couldn't see the shape of the volcano, we picked up a sample, said, what type of volcano might this be? Well, it could be a cinder cone, it could be from a shield volcano, it could be from a lava flow, but this is a fairly non-violent event because the color, being very mafic, is telling us low viscosity, generally not very violent, right? And so here's kind of some properties of that. And then as we cruise on, we can once again say there are some examples. This is a cinder cone, cinder cone, cinder cone, cinder cone. Where did these show up? All right, this is the one that has not a specific home anywhere, really. So a lot of plate tectonic settings, we might get a dominant feature. Like, let's say we have subduction and we're subducting under a continent and we're making intermediate volcanoes. I haven't got there yet. We're almost there. All right, bear with me. Okay, we can also make little cinder cones. Why? Well, this is that variability that we talked about. In general, at that plate boundary where you have subduction under a continental plate, you're going to get intermediate volcanoes. But you can get these little cinder cones popping up too because the magma chamber is changing in composition after every eruption. There's new material coming in, all this kind of stuff. So in association with these big intermediate volcanoes, you can get these little cinder cones. They can show up in, shield volcano areas too, right? So they're kind of a little subset of the main type of volcanoes that show up in certain places, okay? So the good news is your answer for that is almost anywhere. We like that, right? Okay, here's the big one, the one that you hear about the most, the one that we're concerned about the most. These are the intermediate type volcanoes. Okay, so these are stratovolcanoes is a term, or composite volcanoes. Either one is acceptable and they are used interchangeably. This is Mount St. Helens. This is most of the Cascade Range volcanoes. And why? This is subduction related, right? We have a ocean plate subducting under a continental plate. We get melting, partial melting of the mantle. What's that composition? It's mafic. As it rises up, it has the opportunity to mix, melt, include the felsic continental crust, which tends to give us a more intermediate type material. And so we tend to get what we call a stratocone or a composite when we have intermediate volcanism. So what does this mean? It means it's thicker. It means that it's got a higher silica content than our cinder cones, than our shield volcanoes. So it has the potential to be fairly violent. But because it's a range here, one of the reasons the word composite is used is because it's built on what you see here, lava flows and more explosive volcanic eruptions. And so it goes through these phases. You can have lava ooze out the top and flow down the sides. But look, it's pretty thick. And so it doesn't run very far and make a broad, flat shield. It makes a more kind of pointy, steeper type of volcano. One you think of when someone says volcano and you imagine it in your head. You're like, oh, yeah, it looks like that picture or that picture. And those are intermediate. But because it has the potential to be violent, it can blow up and, of course, devastate part of the area. But this violence of explosiveness can shoot material up into the atmosphere, and it falls back down and builds some of the cone shape of the volcano, if it doesn't completely destroy the volcano, right? And so we have these different types of hazards here because it has the potential for violence. Yeah, we have lava flows. Do they run really far like in Hawaii? Because Hawaii is a more shield, mafic, runny volcano. Nope. So they don't go very far, but obviously they're still a hazard. But here I have a explosive hazard. This can blow up and do some damage, right? Throw material a decent distance. But in addition, it has what are called pyroclastic flows. So these are just hot ash and material that run down the side of the volcano. Those can go for miles. We've got what are called lahars. These are mud flows initiated by a volcanic eruption. They race down the sides of the volcanoes and find streams and can travel very far. We have ash being thrown up into the atmosphere, really tiny pieces, sometimes miles and miles into the atmosphere. And those drift with the current of the wind, and they fall back down in blanket areas like a snowfall. And sometimes it can be just a little bit, but if it's a very violent eruption, you can pile up some pretty steep amount of ash. So it has the potential to impact lots of people because it has a wider range of hazards, I guess, right, that can reach farther out. Now, is it the worst? Well, no, we haven't got there yet, right? So the biggest eruptions, the scariest ones, are the last ones we're going to talk about called caldera types, which are very felsic. But those are rare. These guys are everywhere. So the Cascades, boom, 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 boom. There's 20, volcanoes in the Cascade Range. The Andes in South America, there's, a whole buttload there, right? Everywhere we have these kind of subductions, which we have a lot, we get a lot of intermediate. So although they're not the most violent, there's so many of them and people live near them that they're the ones we kind of focus on and the ones that we're worried about the most because of they're so prolific, right? They're everywhere. So same thing. If you were asked, hey, where would I see a intermediate type or a stratovolcano? We're thinking subduction, right? We're thinking one plate subducting under the other. And here's this example of the Cascade Range, right? These are all kind of volcanoes. Boom, 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 boom. These are all intermediate, okay? And so this is kind of where we think, once again, can I get something that's a different composition here? Yes, there's variability. Can I get our favorite cinder cones here? Sure, they can show up here. But the dominant amount of material being erupted here is intermediate because of subduction. Now this other stuff, this green stuff, that's not related to subduction here. This is another issue we can talk about later, but it's not related to the Cascade Range here, okay? And so these are volcanoes we're talking about, right? And there's volcanism in other ways, shapes, and forms. These are called flood basalts. And so, but here we're kind of focusing on volcanoes. So these would be the stratos. Once again, intermediate composition. Why? Subduction is usually the place we see them. They have a range of violence from not too bad to pretty darn bad, right? Where we're worried about them, and they impact society. And they have a huge range of hazards. Mud flows, pyroclastic flows, ash fall, lava flows, all these things we're concerned about. And these are the things we want to mitigate, help fix, help keep, to a minimum when we talk about in the next module, right? Okay, what else I got for you? Oh, Arizona. Are you kidding me? Arizona's got everything. There are actually composite volcanoes. There is this one here, San Francisco Peaks. If you have gone skiing up in Flagstaff, you are skiing on a composite volcano. Intermediate for the most part. Now look, there are also cinder cones all around San Francisco Peaks, kind of to the northeast of the San Francisco Peaks. There's basaltic, right, very mafic lava flows in this area. So it's rare you're going to find an area that just has one thing and nothing else, right? Because this variability of the eruptive material, it changes after each eruption, all that kind of stuff. But this steep-sided kind of feature indicates a intermediate type volcano. And in theory, the argument is that the peaks, if you see this picture here, probably extended up to a kind of more point, like a pier, but this material was blown out kind of like Mount St. Helens, a very violent eruption. No longer active and all that kind of stuff, okay? So there's an example in Arizona. And just to give you some relationship, so here's our intermediate, kind of the size of these features that we see, right? Compared to a cinder cone, look how tiny that is. But if we were going to take this lovely intermediate volcano like Mount St. Helens or Mount Rainier and plot it against, a shield volcano, we can see even that size. And the shield volcano is so big just because it's runny. The lava and material coming out is very runny and can run for long periods, or long distances, sorry. And so that's why they get this broad, flat shape. Okay. Not sure why that's there, but it's illustrating where we get volcanism, right? Divergence, we get hot spots, we get subduction, all that kind of good stuff. Okay. Oh gosh, I forgot about lava domes. No, I didn't forget. They're here, and we got to talk about them because we're moving down the list to our from mafic all the way to felsic. So felsic here, we have these things called lava domes. How do we know they're felsic? Look, the rock is very light in color. A very low amount of mafic minerals, so we know that this is very felsic. It has the potential, because we know it's thick and gooey, it could be violent, but in this case, they vary, right? So it depends on the gas content. If there's a lot, they can be, but they're typically smaller features, and they're usually in association with an intermediate type volcano. And so here you can see that this dome is in a crater, but the overall feature, this is an intermediate volcano. So what is happening here? It's that whole idea of the variability of the magma chamber. Yeah, we get these eruptions because we have an intermediate style, but after we erupt, we change the composition of the magma chamber. Maybe it shifted a little felsic, and so now I get a felsic eruption. Now it shifts a little bit more to the mafic. So there's some variability here. They tend to show up in association with these intermediate. And this little blobby here, that's a dome. That's a lava dome, okay? Right here, lava dome. Right there, lava dome. What's the hazard here? The hazard is not that it's going to blow up because the explosivity is kind of low. Why? Because of this. You usually have a low water gas content. The hazard is that they are unstable. They're so thick and gooey that they form really steep-sided little domes that can collapse on themselves. And then they tumble down the mountainside and they form what's called a pyroclastic flow. And of course, that's bad. And it has some speed to it. It usually doesn't travel super far, but that's one of the bigger hazards here. So where do we see that? There's some variability here, typically in a convergent plate boundary because it's usually associated with intermediate. I don't have a dome for you in Arizona, sorry. Now, the last one we're going to talk about is what's called we're going to call it, in this class, a caldera type volcano. What does that mean? Well, the reason we're going to use that terminology is because the term caldera is really just a descriptive term talking about a collapsed feature. You can get a caldera in other volcanoes. Okay, you can get them in intermediate. It's a feature. It's the crater at the top of the volcano. So you can either get the crater from an explosion, right? Like Mount St. Helens blew its top, we have a crater. Or from a collapsing of the volcano. So why would the volcano collapse? Well, the story is that in this image here, you see a magma chamber down here. As that magma chamber is pumping material out of the volcano, it's removing magma deep in the earth and creating basically a hole, a pocket that can cause the overlying material to collapse down into it, forming this crater. And so the term caldera does and is used to describe this collapse feature. What we're going to say is, yes, that's true, but there are these certain types of volcanoes that are called caldera type volcanoes that are so massive that the only thing that's left of the volcanic event is this huge collapse feature. So it's not a small feature at the top of a volcano. It's a feature that encompasses this huge area that's 10, 20 miles across, and it has obliterated most of the evidence of a nice steep-sided volcanic system because it was so violent. And why was it so violent? Because of its composition. So here we have something very felsic, but there's a lot of dissolved water and gas in here. So usually when we talk about things like this, we reference Yellowstone. Yellowstone is a hot spot under the continental crust. And in this particular case, there's some melting going on, but ultimately you're ending up with a big magma chamber that's full of very thick, gooey magma that's very felsic, and a lot of water and gas dissolved, which means that it can't escape. And the pressure in this huge magma chamber is enormous. And so what happens here is when there is an eruption, it is so violent and there's so much power that you empty almost the entire magma chamber, which is fairly large, and you get a huge collapse after the fact. These are super violent. They have the potential to be, planet altering, and the material they eject can affect climate and a huge area. And so there's evidence that Yellowstone has erupted very violently in the geologic past, produced a huge amount of material, places where there's tens of meters of ash piled up from material being ejected out into the atmosphere and then falling back down, right? So these are, and of course the material stays in the atmosphere, it blocks sunlight, and it can have a pretty big impact on our planet. So these are the scary ones. And of course, if you watch Discovery Channel, they're telling you we're all going to die from Yellowstone or something like that. Humans have never experienced, to our knowledge, a super volcano eruption, which is what these caldera type eruptions are related to, right, and are associated with. We have evidence. Oh crap, here's some here's some volcanic material that we can tie back to Yellowstone. Chemistry helps us with that, things like that. So we can say, wow, this material came from the source, and it covered, hundreds and thousands of square miles, half the continental US. That would have a big impact on society if that happened. So we know that they exist. We know that they can happen. They're not as common, of course, as our intermediate. So we focus more of our energy on the intermediate volcanoes and how we can mitigate those hazards. We talk about the caldera types in awe and like, holy crap, that would be amazing if that happened, and horrible at the same time. But these are the big super volcano things, the stories you may have heard or read about or watched videos about, right? So it is why? Well, composition, right? Very thick and gooey and lots of water and gas dissolved. That combination is a problem. And how do you know that it was felsic? Look, it's light in color, right? Light in color. So this is potentially ash deposited. Look how thick that is and how many layers that is. That's a lot of material coming out of a volcano and falling back down into layers. Of course, it's been squished and altered because it's, been through some stuff. But this is a lot of material coming out of a volcano that has an impact on our planet. But you can look at it and say, hey, this is light in color. This is felsic. This might be from a very violent eruption, right? So you can, just by looking at its color for us at this level, we can make some interpretations about that observation. And yes, believe it or not, there is a couple actually examples of calderas, the Superstition Mountains. And here's this example. If you're from Arizona, I apologize if you don't know anything about Arizona, but in Arizona we have this mountain range called the Superstition Mountains. If you go out there, there's a man-made lake plopped in there. If I said, point to me, where's the volcano? There's no steep-sided volcano that we typically associate with volcano shapes. Why? Because this thing blew its top, exploded, obliterated most of the features associated with a nice, steep-sided volcano and collapsed into itself and formed this rugged terrain. Of course, it's been beat up too because it's, 17 million years old. But these are layers here of ash deposits that exploded out and fell back down and kind of formed these layers. This is the remnants. This is how we know there was a big violent eruption here, because we can look at these and say, oh, they're volcanic. There must be a volcano here. And we look at their composition. Oh, they're very light in color. They're very felsic. Where's the volcano at? We start to piece things together and come to this conclusion that this was a big caldera type eruption, super violent, lots of collapsing, lots of obliterating of the topography, lots of material ejected, lots of deposits of stuff. It's a bad day if you're around this area for sure. Okay, so those are all calderas. Oh, all right, so we're back to this. So those are the volcano types I want you to be aware of, okay? And this is the same thing I introduced. This is what we've learned, right? There's shield volcanoes, there's cinder cones, there's stratocones, there's calderas, and there's domes. In general, we can walk them down the composition scale. Shields are up here in mafic. They have low silica, so low viscosity, not very violent. They tend to form in these hot spots under the ocean, also in some divergent plate boundaries. As we move down the composition, we get cinder cones. Where are those guys? Freaking everywhere, right? So, all right. Intermediate, here's our main kind of volcanoes that we see in the world today. Why? Because of convergent plate boundaries and subduction. This is where we get the partial melting of the mantle, the rising of that material, the mixing, all that good stuff. And so we get stratocones or composite, that's acceptable. It's in the middle of our, silica content percentage, which means it can be down here a little bit and not be very violent. It can be up here and be pretty darn violent. And so this is how we build our intermediate. It's the typical shape. And as we move down to the felsic composition with high silica content and a very high viscosity, we get these little domes, which we kind of, a little side note that kind of pops up here and there. Yeah, okay, but the caldera type volcanoes, ooh, we're scared of those. Those are the big super volcanoes. Those are the ones that do lots of damage. Why? More power, right? There's more explosiveness here. That power has the ability to inject much more material out. So if it's out, it's either in the atmosphere and it's causing havoc there, it's falling back down, causing havoc there, or explosions are racing the material outward from the event and causing hazards there. This is where our big super volcanoes are problematic for more people, but they're rare. So am I worried about this killing everybody or these? For now, it's these because they're so common. Hundreds of them around the planet, and they're erupting all over the place. So I'm always monitoring and I'm always concerned about these. Okay, I'm concerned about these, and these make for cool stories and great videos and things like that. But they're rare and they don't happen very often, right? And so that's going to put that in perspective. All right, and what else? Just wrap it up. This is from your igneous rock lab. We can play the game, right? These are the rocks that we should see associated with our felsic types of volcanoes. Rhyolites. Why? Because these are the stuff that's to the surface. gets to the surface, it's fine-grained, it's small crystals. So I should see rhyolites if I'm looking at felsics. What if I'm looking at intermediate volcanoes? I should see andesites. If I'm hiking Mount Rainier, I should see andesites or somewhere in there, right? There's dacites and things like that, but it's intermediate. What about if I'm on Hawaii? I'm looking at a shield volcano. I should see lots of basalts. What color should they be? They'll be dark black, right? Because that's what I expect. So we were taking these things, right? Color, shape, size, and we can even talk about, like we just did, where these come from. What's causing the melting here? Why is there a volcano here? We can explore that because we can look at the composition and we can associate that with specific volcanoes, specific features, specific hazards, eruption styles. That's the game we want to play. That's what we want to figure out. All right, so that's what I'm expecting you to kind of know about this module. And then next module, we will talk about more of the hazards, right? We'll investigate each hazard as it associates with the typical different volcano types. Okay, hopefully that was helpful. And what else? I think that's all I got for you. So if you have any other questions and you want to reach out to me, please feel free to do that.